Good day, sir. My name is Luis Montemor, a student of ENE161, and today I'm going to present to you machine problem number 3. The problem that I'm going to discuss today is from Heath's second edition, problem 9.6, which is about the Lorenz attractor. So for table of contents, in this report, I'm going to talk about 4 things. Number 1 is the brief overview of the Lorenz attractor. Number 2 is the source code of the NetLogo. Number 3 is the systems dynamics modeler for NetLogo and Vensim. And number 4 is our observations and the discussion. So overview of the Lorenz attractor. So Edward Lorenz is a mathematician and a meteorologist, first studied the Lorenz system, which is a system of ordinary differential equations. So it stands out for having chaotic solutions for specific parameter values and initial conditions. So the Lorenz attractor, in particular, is a collection of chaotic Lorenz system solutions. The butterfly effect in popular culture, which is based on real-world implications of the Lorenz attractor, which states that in a chaotic physical system, without perfect knowledge of the initial conditions, our ability to predict its future course will always fail. So what is the relevance of this problem in environmental engineering? So the relevance of this atmospheric model in environmental engineering is that this is closely connected and related to meteorology, which is a branch of a geoscience that's related to environmental engineering. The Lorenz model can be used to predict weather and climatic patterns. So the following systems of ODEs, which is the 9.6 problem formulated by Lorenz, represents a crude model of atmospheric circulation. So we have 3 systems of equations here. Y prime 1, which is given to us by sigma, y2 minus y1, then y2 prime, which is r, y1 minus y2 minus y1 multiplied by y3, and then y3 prime, which is y1 y2 minus b y3. So in continuation, we're going to take sigma, which is a value of 10, beta, which is a value of 8 over 3 or 2.667, and a rho value of 28. So we have to get the initial values, and we have initial values rather of y1 of 0, y3 of 0, which is equals to 0, and y2 of 0 is equals to 1. So we need to integrate this ODE from t is equals to 0 to t is equals to 100. So this is our limit. So we need to plot y1, y2, and y3 as a function of t, and also plot each of the trajectories of y1 and y2, y1 and y3, and y2 and y3 as a function of t on a separate plot. So this is the source code for the NetLogo. So this is the systems dynamics modeler which I used in Vensim. So as you can see here, y1 prime enters y1, and which is connected to the values over here. So in hindsight, it is set the same way as NetLogo, which I demonstrated a few weeks ago. So the values over here is oriented similarly as Vensim. The initial values are still stored inside the flow arrows. So this is the result after running the simulation through Vensim. As you can see here, that the values of y1 and y2 and y1 and y3 and y2 and y3 are similar as how we run it through Vensim, through NetLogo rather. And you can see here the sums of the plots. As for the NetLogo, you can also see here this one is a much smoother trajectory, since we use a dt value of 0.01. So it is still oriented similarly or in the same manner as the simulation in Vensim and the simulation for NetLogo. So for this one, we use 2 references, one paper from Lorenz and one paper from Salzman. So this concludes my report for today and my report for machine problem 3. Thank you so much, sir, for being our instructor for this semester, and thank you so much.